You've already learned about inertia. Now remember that Aristotle thought that, well, he thought some correct things, like he divided the universe up into forces on one hand and matter on the other. Forces are the things which cause matter to move. Aristotle thought that things tend to come to rest on the Earth, which we know is wrong. Galileo discovered the law of inertia, that things, if they have no force on them or they have balanced forces, then they just tend to maintain their straight line motion at a steady speed. That's the inertia law that Galileo discovered. Newton made it more correct and precise, and we now know it as Newton's first law, that an object will move in a straight, steady line if there's zero force that acts upon it. What if there is force that acts upon an object? Then how does it move? Like kicking a ball. We know what happens. It's at rest. During the kick, it changes its state of motion. It doesn't stay at rest. Now it'll gain speed. So making that precise is what Newton's second law is all about. And that's what chapter 4 is, Newton's second law of motion. Let me remind you that you should be reading the text in addition to the videos. And at the end of each chapter, there are review questions. After reading, check those review questions so you know that you have a good grasp on the material before you start the homework problems. Okay, so Newton's second law, we'll learn about how force causes acceleration. We already know that no force means that an object maintains a steady motion. Well, if there is a force on an object, like when you kick something, during the kick, the ball accelerates. And we'll see how to predict what the acceleration would be. Then we'll learn about friction, and we'll be sure to distinguish again between mass and weight and learn how to measure the weight of something. And we'll put down Newton's second law of motion in detail. We'll talk about free fall and non-free fall. In other words, air resistance. What does terminal velocity mean when someone's skydiving, for example? Let's remember what force is. When you hear force, you think of Star Wars, the Force. That's a kind of force that acts at a distance, a special kind. But force is just really any push or pull. It could be from a rope. It could be from gravity that acts at a distance, like Earth's gravity does pull on the moon very far away. Examples are tension, and remember a string stretches when you pull on it and the ends pull inwards. That's tension. Support is whenever you touch a surface, there's contact that's produced. The atoms compress, and that produces a support or normal force, we call it. Support force, also known as normal force. And then gravity acts at a distance, and we'll learn about friction. Like if you slide across the floor, you'll slow down because of friction. Newton's first law again, that's the inertia law. It says that if there's zero force upon an object, either because there just are no forces on it, like it's off in deep space gliding along, or if the forces are balanced, like I'm sliding across ice, then there's no friction. My weight is balanced by the support from the ice. That's just balanced forces. Either way, if there's no force upon an object, then the object maintains uniform motion. In other words, straight line motion at a steady speed. Remember the motion diagrams. If I slide along and I drop breadcrumbs behind me, I'll drop them evenly spaced. Like if I drop one every second, they'll be evenly spaced. And that's how I could tell that I'm in uniform motion, and there must be then no force upon me. It really goes both ways, by the way. If the force is zero, then there's uniform motion. Also, if you ever see something in uniform motion, then it must be that there's no force upon it. Remember that there are two kinds of equilibrium. There's being at rest, which we call static equilibrium. If there's no force on a thing and it's right now at rest, it'll stay at rest, like the chair that you're sitting on. But also there's what's called dynamic equilibrium. That's like if I glide across the ice, I'm moving, but I'm still in equilibrium. It's just that I'm maintaining my speed because I have no net force on me. Forces on me are balanced. That's what we call dynamic equilibrium. Now, to get us thinking about what happens when there is a force on an object, when the forces are not balanced, just so we have a picture in mind, let's look at a bowling ball hitting a pin. Okay, and in picture A, all the forces are shown on the ball. There's the weight of the ball, let's label it weight, and there's an upward force from the floor. We call that the normal force or the support force. They're in balance. The ball's gliding along straight and steady, and that's because the forces on it are balanced right now. I'll remind you that the support is actually coming up from underneath the ball, but we draw it as if it comes from the center just to show how it balances out the weight. So now in picture B, it's actually striking the ball, and I want to draw the forces again. Pause it for a second. Think about now what changed. Are there more forces on the ball now? And what are they? Okay, I hope you thought about that. And let me give the answer. The ball's weight is no different. Earth's gravity didn't change just because it's hitting a pin. It's still in contact with the floor, and the same support is still there. So, and the normal force didn't change either. The difference now is it's striking the pin. There's contact being made with the surface. That means there's another normal force that's from pushing against the pin. Which way does that force point? To the right or to the left? Well, I'm looking at the force on the ball, and the ball pushes against the pin on the side of it. The pin pushes back to the left on the ball. I'll call that force S, just to give it a name. It's the force from striking the pin. It's really just a contact force from the surface. It points to the left. Now, the pin has a force to the right on it, but we're just drawing a free body diagram, freeing the ball from everything else and just drawing the forces on the ball. Okay, so there's a force to the left on the ball. Only during the moment it contacts the pin. Once the pin goes flying off, like in picture C, then we're back to just the weight and the normal force. Just like it is in picture A. Now the ball is slowed down between A and C, but the only slowing down that occurs is in picture B. Notice only in picture A, isn't the net force equal to 0 on the ball? Sure it is. Up cancels down, 0 force. In picture C, isn't the force 0 on the ball? Sure. They're both equilibrium situations. What about picture B? Is the net force on the ball now 0? No way. The weight and the normal force do cancel each other, but there's an unbalanced force left over on the ball, which points to the left. The net force on the ball sure isn't 0 in the middle picture. That's when the ball is slowing down, not maintaining uniform motion, right? Okay, so from this kind of experience with like a ball colliding with a pin, something like that, we know that force causes, in that case, it causes the ball to slow down. What do we call slowing down? Deceleration, right? But in general, force, like if you kick a ball, that would make the ball speed up. In general, forces cause acceleration. And you know that a little bit of force on a ball, it'll cause only a small amount of acceleration. Like if I have a bowling ball there and I just push it with my finger, the ball will pick up speed and then glide along. But the little push I gave with my finger is only going to cause a small acceleration. That's little force acting on the ball. That's going to cause very little, or small force causes small acceleration. If you hit the ball like you have a golf ball and you hit it very hard with the golf club, then you're going to have a very large acceleration. If you bunt the baseball versus take a full swing at it, the ball experiences a much larger acceleration if you hit it with a larger force. Okay? What about the motion diagrams? Let's just remember that as the force acts on it, that's when the acceleration occurs. If there's no force on it, then it's just gliding along. Okay, so the ball's at rest, the force then acts upon it, so now the ball is going to gain speed. Means it'll go faster and faster from one moment to the next, gain distance at the according to our kinematic equations. Now, if the force on it is larger, then it'll cover much more distance in the same amount of time, and its motion will look something like that. Small acceleration versus large acceleration. In fact, force causes acceleration. It turns out that the acceleration that occurs is directly proportional to the force. If there are multiple forces on the object, the acceleration is directly proportional to the net amount of force, the total amount. Remember when we calculate net force on things, like if you had 20 this way and 10 that way, you have to do a subtraction to get the net amount. So you have to look at the net amount of force on an object, not just one of them, but all the forces that act upon it to learn how the object's going to accelerate. And when we say it's proportional to the force, what that means is if you double the amount of force, the acceleration will double. If you apply 10 times the force, like you take a full swing against the ball versus bunting the ball, then if it's 10 times the force, it'll be 10 times the acceleration. To say it a different way, to increase the acceleration of an object, you have to push harder. You must increase the force. Okay, now there's another ingredient that matters. Let me illustrate that. A lot of these these laws of motion are best illustrated in zero gravity situations, because then there aren't a lot of extra forces that could complicate things. Here, in a zero gravity environment, he's blowing as hard as he can on these 3 balls. Which ball do you think has less mass? I think you would say the top one, the one that looks like maybe it's a ping pong ball, that one has less mass. And how do you know? Well, because he's pushing on it with his breath. He's blowing on the ball, pushing on it, and look at the huge acceleration that ping pong gets. Ping pong ball has a huge acceleration because its mass is very small. The metal ball that has a big mass on it, it hardly accelerated while he blew on it. It did accelerate a little bit, but it barely gained any speed, right? This is an illustration of the fact that the more mass an object has, the less acceleration it will get when you push on it. Another example is if you try to ram into an elephant, you're going to get bowled over. The elephant hardly moves. Elephant has more mass. When you apply force to something with a huge amount of mass, it barely accelerates. Okay, so the point is larger mass accelerates less. If you punch a ping pong ball, it will have a large acceleration and it goes flying off. Now remember, I'm assuming the force keeps acting on the ball and it keeps accelerating. Once the force goes away, it doesn't accelerate anymore, it just glides, cruises along. If you apply that same force to a bowling ball, then it will accelerate, just very, very little acceleration, barely gaining any speed. Just like the astronaut blowing on the metal ball, barely gained speed. So you see, mass resists the effects of force. Force tends to get things moving, but not if the thing has a huge mass. It barely gets moving if the mass is huge. So mass resists acceleration. And you know all about that. You can throw a golf ball easily. Throwing a football takes some athleticism. The football has a much larger mass, and you really have to put some muscle into it to throw it. So, saying it a little more precisely, the same force applied to twice the mass produces half the acceleration. If it has 3 times the mass, it's even harder to get it moving, and it'll only have 1/3 of the acceleration. This is how it works from careful experiment and measurement of these things. So now let's put down Newton's second law in precise detail. Remember, the first law is just that if there's 0 force on a thing, then it has no acceleration at all. It just moves in a straight, steady line. If there is force upon an object, then we've just seen that it accelerates. The acceleration that occurs is proportional to the amount of force that acts on the object. So you got to add up and find all the force that acts on the object, but you divide by the mass of the object. That way, if the mass of the thing is huge, the acceleration will be super, super tiny. Think about this when you look at the balls being blown away. Same force essentially acts on all 3 of them, but with that heavy ball having a very large mass, it barely accelerates. Another way to rearrange it is to say that the net force on an object is equal to the mass times acceleration. 2 versions of the same equation. The first one is useful if you know the amount of force on a thing and you'd like to predict how it's going to accelerate. Like you have a car, you know the mass of the car and you know how much force acts on it. What's its acceleration going to be? The second version is useful if you know the acceleration already and you stick it into the equation and you could say, oh, now I know how much force must be acting on it. Let's review some terminology I've been using. Directly proportional. I said that the acceleration is directly proportional to the force on the object. That means if the force goes up, the acceleration goes up too. Big force, big acceleration. However, acceleration is inversely proportional to the mass of the object. We saw that in blowing the balls away, right? Big mass produces small acceleration. If the mass is big, then the acceleration is actually less. Doubling the mass gives you only half the acceleration. That's inversely proportional. Okay, let's get some practice with this and practice with some of the techniques that are used. Suppose the hand is accelerating the brick. Let's forget about any kind of friction. The brick is gliding along a super smooth surface. So the only force that acts on the brick is the hand. Okay? So we would say that the acceleration of the brick is equal to however hard they're pushing. Now, how in the world could you measure how hard you push on a thing? Can you think about that for a second? Couldn't you push onto you can stand on a bathroom scale, it'll measure your weight, right? You could also just like sit next to it and push on the floor with your arm, and the scale would register how hard you can push. So you could use a scale and measure how hard of a force you can push with. Maybe you can push with, I don't know, 50 pounds or whatever from each arm. Okay, so the acceleration of the brick would be equal to the force that you can apply, 50 pounds of force or whatever, divided by the brick's mass. The brick has mass, and you have to divide by that mass to predict the acceleration. Now, what happens if you push with both arms? That's going to double the force, right? In this case, just F, but in this case, double the force. It's acting on the same mass, though. Now, what's the acceleration going to be? Let's see. Make a guess before we work it out. Double the force, what's the acceleration going to be? Okay, so to figure it out, I have to take the net amount of force, which is now 2F, and divide it by the mass. Okay, now if this is the acceleration produced by one arm, let's call this A2, the acceleration produced by two arms. It's double the force divided by the mass. But isn't that just 2 times what the previous expression was? 2 times F over m? And isn't F over m just the original acceleration, A1? In other words, we've just spelled out the procedure for figuring out the acceleration compared to what it was with only one arm pushing. The acceleration with 2 arms is twice the acceleration that you get with 1 arm. This technique that I showed you is very useful because, I don't know how big F is. I don't know if it's 50 pounds or somebody super strong is 100 pounds or whatever, but the point is you can still understand how the acceleration changes without knowing the actual, numbers that are involved. What if it's twice the force, but acts on 2 bricks? Pause it, work it out yourself. Okay, welcome back. I'm going to give the answer. This is the acceleration with now, I'm going to call it A3. But it's the acceleration with 2 arms pushing, that's 2F for the net force, divided by the total mass of the object, which is 2m. And algebra, if I have 2 divided by 2, that just cancels, and I just get F over m again. And isn't F over m just the original acceleration of 1 arm pushing on 1 brick? Yes. So if you double the force, but you also double the mass, then it's no difference. The motion that's produced is the same. Make sure you get how these work and how you can solve the problem without knowing what the actual masses are and what the actual force is. You have to be comfortable with the little bit of algebra involved to set it up. Okay, a couple more. This was 1 arm pushing on 1 brick, and we call the acceleration there A1, F over m. What if it's 1 arm pushing on 2 bricks? Let's call that one, I'm going to just rename everything. Let's call it A2. Well, it's the same force, but now it's twice the mass. 2m is the mass. And isn't that just 1/2 of A1? So in other words, doubling the mass produces 1/2 of the acceleration. 3 bricks, m, and m, but 1 arm pushing. Let's call that one A3. It's the same force F, but now 3m is the mass. And so that gives me 1/3 of the original acceleration. In word problem form, suppose a cart is pushed along a track with a certain force. Again, forget about friction for now. If the force remains the same, well, the mass of the cart decreases. There's a bunch of, sand in the cart, or you have a bunch of water bottles in the cart and a bunch of them burst open, and the water spills out. If you keep the same force while you push on it, but the mass drops by half, what happens to the acceleration? Pause it, work it out using the techniques that I just showed you. Okay, welcome back. I'm going to figure out the acceleration now. The force, so there's the original acceleration, which is just the original amount of force divided by the mass of the cart and its contents. Now, if the mass of the cart decreases to half, let's call that the new acceleration, A2, it's the same force. You're pushing just as hard as you can on it, like you're pushing with 100 pounds of force on it. But now the mass has reduced to m over 2, half the mass. And I know that you know your algebra, dividing by a half is the same as multiplying in the numerator by 2. So there's just 2 F over m. And isn't that just twice the original acceleration? Giving us the answer is C, that it doubles. So decreasing the mass, we know that increases the acceleration. In fact, it's like if you hit a golf ball versus hitting a bowling ball, it'll have the lighter thing, this less massive thing has a much larger acceleration. Here's just the technique for working it out in detail. Suppose you're pushing a cart along a track, so twice as much net force acts on it. So now you've doubled the force, but somehow the acceleration remained the same. How in the world could that happen? The answer is if you double the force, so the acceleration, you're doubling the force. How could the acceleration remain unchanged? Most likely it's because the mass doubled. That's the simplest explanation. If the force and the mass double, then it's just the original acceleration again. So that'd be the most likely explanation. The mass doubled when the force doubled. So you're pushing the cart, then you push twice as hard, but a bunch of sand fell into the cart and doubled its mass. Then it would be just going just as fast. I should say it's going faster and faster. It is accelerating, but the acceleration is the same. You doubled the force, but guess what? The inertia doubled too. It was Newton who first connected the concepts of mass and force to produce acceleration. That acceleration is equal to the net force on an object divided by the object's mass. Okay, so we're familiar in the United States, we're familiar with measuring force in pounds. That's not the metric unit of force, however. The metric unit of force is a Newton, named after somebody you might have heard of, Isaac Newton. How is 1 Newton defined? Like, how's the definition of it cooked up? How big 1 Newton is? It's a push or a pull. How strong of a push or pull is it? Here's the answer. If you take a 1 kilogram mass, I hope you remember what a kilo is. 1 gram is the mass of a cubic centimeter of water. Take 1,000 of those and you got 1 kilogram. Okay, 1 kilogram, so it's like a little, I don't know, like a little one of those mini watermelons or something. 1 kilogram, and you push it along. You put it on ice, and you push it so that its acceleration is 1 meter per second squared. And you use a force measuring device to measure how hard you're pushing it. Okay, the force required to accelerate 1 kilo at the rate of 1 meter per second squared is 1 Newton. 1 Newton, so that's how it's defined. It is equivalent to about, roughly speaking, a quarter pound. Okay, so the weight of a quarter pound burger is about 1 Newton of weight. Okay, or another way to remember it is the weight of an apple is about 1 Newton of force. You feel that weight in your hand, that's about 1 Newton. Newton and the apple, we'll come to that story later, but okay. Let's be sure that we're not confused about weight versus mass. They are not the same thing. I'll give some examples. One example is if you take an anvil. You know what an anvil is? An anvil is a giant mass which metal workers, blacksmiths use to hammer stuff on, right? The huge iron block, basically. It has a huge mass. In space, it weighs nothing. Does that mean it's massless now? If an anvil comes flying at you in space, do you duck? I hope so, because it sure has mass and it will sure hurt you if it hits you. However, you can lift it up over your head, no problem at all. Okay? So it absolutely has mass no matter where you take it in the universe. but it won't necessarily have weight. So the anvil weighs nothing in space, but it still definitely has a whole bunch of mass. Okay. Another example to distinguish mass versus weight. Well, like these, for example, these balls are in a zero gravity environment. They're just hovering, floating there. Do they still have mass? They obviously do, because look at that metal ball. He's pushing on it, but it's demonstrating its inertia, its mass. It's resisting acceleration because of its mass. A giant ship is tremendous weight. No way anything could lift that. I mean, basically impossible to lift. Huge weight, but you can still push it around. A tugboat can push that thing around, demonstrating that weight and mass, they're not the same thing. Similar idea with a car. You would not be able to lift a car because of its huge weight. But if the car runs out of gas, you'll be able to get behind the car and push it along level ground. I'll come back to some examples. Now let's discuss friction.